All right, so here in lesson 26, what I want to start off with is a quick review of the type of thing that we did on Monday. All right, finding the extrema of a function on an interval. So here we have the function 2 sine x minus cosine of 2x is f of x. And our interval that we're working with is the interval from 0 to 2 pi. Okay? So the interval from 0 to 2 pi. So the first thing that we can do is get our two endpoints. All right, that's pretty easy. So we plug in x equals 0, plug in x equals 2 pi. What's sine of 0?
0.
0. Cosine of 0 is 1. So we have 0 minus 1. So the point here is 0, negative 1. Okay? And the nice thing is with 2 pi, it's coterminal to 0, so that's going to give us the same values for the trig functions. So it's also going to be negative 1. So 2 pi negative 1 is our other endpoint. Okay? We might have had one similar here. So we have a choice here when we're trying to find our critical numbers. We know that cosine and sine are continuous for all real numbers, so we're not going to get any from where the derivative is undefined, because these are continuous everywhere. They're going to be differentiable everywhere. So we know the derivative is going to be defined for all real numbers as well. So we need to take the derivative, and eventually we're going to set it equal to 0 and solve. As you guys know, when you're setting something equal to 0, you're not going to be able to solve an equation that has a trig function that has just an x in it and another trig function with a different thing inside of it. So we're going to need to use the double angle formula at some point. I would recommend, particularly in this case, waiting until after you take the derivative to use the double angle formula. Okay? If I use the double angle formula right now, I'm going to have minus cosine squared plus sine squared. And then I'm going to have to use the chain rule a couple of times when finding the derivative there. Okay? If I do the derivative as it is right here, f prime of x is going to be 2 cosine x minus derivative of cosine is negative sine, so that's going to be a plus sine of 2x times the derivative of 2x, so that's going to be times 2. Okay? Just using the chain rule here. Now, at this point, if I'm going to try to solve this for when it equals 0, I'll need to use the double angle formula. Now I'm going to do it for the sine of 2x. Okay?
Why isn't it minus?
It's not minus because it originally was minus and then the derivative of cosine was negative. Okay? Yeah, we can't subtract 2 sine of x and then divide by cosine and have like tangent equals 1, because it wouldn't be tangent because the angles are different. All right? That only works if the angles are the same. So what we're going to do here, I'm going to plug in a 2 sine x cosine x for the sine of 2x. So I have a 2 cosine x plus 2 times 2 sine x times cosine x.
So you can factor out cosine.
Yeah, so now we can factor out, I'm going to factor out a 2 cosine, and I'll have a 1 plus 2 sine x equals 0. Huh?
1 plus 2 sine x. I was just thinking that 1 plus 2 sine x equals cosine.
Oh, no. No.
So we can just say 2 cosine x equals 0, divide 0 by 2, and do the same thing if
Yeah. Exactly. So that tells us that either the cosine of x equals 0, or the sine of x is going to be a negative 1/2. Okay?
What happens to the other cosine x x, the one that you're adding.
I factored it.
Yeah.
Factor it out. Yeah. All right, so now here we need to know our unit circle. And by the way, guys, if you have not already been doing this, the unit circle is not going away. All right, so when you're doing your homework and you run into a trig problem, try to do it without your calculator. Okay? Try to do as much as you can just with the unit circle. Even if you have to pull up the unit circle and look at it, get used to using the unit circle because you're going to have plenty of trig on the no calculator parts.
Yes, no calculator.
All right, so, and that's not going to change, all right, just because you don't like it, maybe.
You choose
All right.
less than the calculator.
So, nope,
Gosh.
nor would I. All right, so,
Oh, that's just me.
where does the cosine equal 0?
1.
Now, cosine of 0 is 1. The cosine equals 0 at pi over 2.
Or 3 pi over 2.
At pi over 2 and 3 pi over 2. There we go. Okay? And then where does sine of x equal a negative 1/2?
4 pi over 3.
Wrong reference angle.
Pi over 3.
Oh,
pi over 3.
No, that's.
Wrong reference angle.
2 pi over 3. It's third and fourth.
It's not over 3. Sine is a half, not cosine.
What is sine actually?
Oh, it's pi over 3.
Negative.
7 pi over.
Pi over 6. Pi over 6.
Pi over 6 is the reference angle. So 7 pi over 6, I'll get to you.
I reversed them.
And 11 pi over 6. Okay? That's alright, you're trying. So now as we're putting them in our table, and if you're making a sine diagram especially, you got to make sure that you do this. Be careful that you put them in the correct order, smallest to largest. Alright? So a half is the smallest, 7/6
I'd be the one that messed
is the next largest, 1 1/6. Then 3 halves, so 1 1/2 is the next largest, and then 11/6 is the next largest. So please be careful that you don't mess that up after you do all the hard work, because that'll definitely mess up your sine diagram. Okay. Now, at this point, the problem asks for the extrema, so all I need are the absolute max or min values. So since that's the case, I don't actually need to do a sine diagram. If I wanted all the relative max or mins, then I would want to do a sine diagram. But at this point, all I've got to do is plug these 4 values in to the original function and see which one gives me the biggest y and which one gives me the smallest y. Okay? Yeah.
Would it be 11 pi over 6 or 11 pi over 2?
6.
Oh.
I did that before too. I don't know what my problem is. Thank you. 6. There. Okay, so now let's evaluate these in the original function. So I have 2 times the sine of pi over 2. Sine of pi over 2 is 1. What's cosine of 2 times pi over 2? 2 times pi over 2 is just pi. What's cosine of pi?
0. No, negative 1.
Negative 1. So I have 2 times 1 minus a negative 1. That's 2 plus 3. Okay, so pi over 2, 3. Alright? So right now that's in the running for our absolute max. Let's see what the other points are. Okay? So sine of 7 pi over 6 we already know was a negative 1/2. And then cosine of 7 pi over 6 times 2 is going to be 7 pi over 3. Okay, this we have to think about a little bit. Cosine of 7 pi over 3, that's past our 2 pi. So that's the same thing as cosine of pi over 3, which is
1 over 2.
1/2. Okay? So you gotta use those coterminal angles in this case here. Alright, so I have 2 times negative 1/2 is a negative 1, minus a half is negative 1 1/2. And that occurs at 7 pi over 6.
Mr. What? Oh, Mr. Hickson, where does 2x in cosine go? Like, where does the 2?
I multiplied 7 pi over 6 by
That's
2,
why
so it's 7 pi over 3. Yeah.
Negative 1 and 1?
Yeah, negative 1.5. Okay, so now I plug in a 3 pi over 2.
That's negative 1.
Okay. Sine of 3 pi over 2 is negative 1, so that's a negative 2 minus, and then cosine of, if I multiply that by 2, it's just cosine of 3 pi, which is the same thing as cosine of pi, which is negative 1. So it's negative 2 minus a negative 1. Well, it'd be plus 1, so it'd take us to negative 1 there. 3 pi over 2, negative 1. Okay? Guys, this stuff is part of what makes calc so challenging, is that there's so many little details. You lose a negative, you get the wrong reference angle, all this kind of stuff. Okay? You got to be real careful with the details. Okay? So then we have 11 pi over 6. Alright, so now let's try this here. 11 pi over 6. 2 times the sine of 11 pi over 6. What's the sine of 11 pi over 6? Negative 1/2. Minus cosine of 2 times 11 pi over 6, which is 11 pi over 3. Okay? So that's going to be 5 pi over 3. That's what it was. We had 4. It was supposed to be 5. Alright, so that's 5 pi over 3. That's what it was. Okay, so now we have a negative 1 minus, the cosine of 5 pi over 3 is in the fourth quadrant, so it's minus 1/2, and we get minus 1.5. There we go. So when we're trying to find the absolute max or absolute min, we're talking about the max or min value of the function. So
when you plug those numbers in, what you get?
Yes, what we get. So the y coordinate is what we're looking at. So what is our absolute max here, guys?
3 pi over 2, 3.
Okay, the max is 3. Absolute max, we'll say. The absolute max is 3, and it occurs at x equals pi over 2. Okay? So that's one thing that we're looking for. That's one extrema. What is the absolute min here?
7 pi over 6 and 11 pi over 6.
Okay, that's where they occur. The actual min is negative 1.5.
So it's at when x equals 7 pi over 6 and when x equals 11 pi over 6.
Yes. Remember, we said you can only have one absolute max and one absolute min, but they might occur at multiple locations. Here's an example where that happens. 7 pi over 6 and 11 pi over 6 both have the absolute min. And if you look at the graph that's been sitting there the whole time, you can see that. So I want to take a step towards our new idea for today by looking at the exploration that's there at the bottom of your page. So in order to illustrate this, what this exploration is asking you to do is, I want you to graph 2 points on the plane here. So the point 1, 3 it says, and the point 5, 3. Okay, so 1, 3 and 5, 3. And then it says, using a pencil or pen or your iPad, draw the graph of a differentiable function f that starts at 1, 3 and ends at 5, 3. I don't care what happens in the middle as long as the function is differentiable and continuous, okay? If it's differentiable, it has to be continuous, right? So, from 1, 3 to 5, 3, draw a differentiable function.
Make a V.
So you're saying make a v?
That is undifferentiable.
Why is that undifferentiable?
There's a sudden change.
All right, yeah. So that one will work. Any other ideas of how we could draw one where we wouldn't get one?
One that like isn't a function.
Well, then it wouldn't be a function.
A straight line.
Okay?
How about one?
A straight line is always zero.
Yeah, that's fine.
How about one?
Okay, what about a straight line? Is there anywhere on there that the derivative is 0?
Everywhere.
How about anywhere on there? Yeah, okay. So, a lot of you had like part of a parabola, or some of you even had, you know, something like this. Okay? But notice, no matter what you do on this, you're going to get at least 1 point. In my case, I have 2,
That's differential.
where the derivative equals 0. Okay? Where the derivative equals 0. So, the answer to would it be possible is no, because if we draw a straight horizontal line, then it's 0 everywhere. If we go either up or down, in order to get back down to the same level, the y equals 3, we're going to have to change direction.
Wait, but what about the absolute value function?
That's not different.
Okay. Well, the absolute value function also, you know, that you've got that v thing going again. So you have that point where it's not differentiable. All right. So this right here illustrates actually our theorem that is the main idea of this lesson, and that is Rolles theorem. Okay?
Wait, so basically all you're saying
guy
is
to
that
think about
if the function is differentiable, there's always gonna be a point where the derivative is 0. This is something
That was a joke, but I'm
Okay.
not.
If
I'm a laugh.
no.
Sorry.
If the function is differentiable and we have 2 points that have the same y value, notice we had 1, 3 and 5, 3. Okay? If that's the case, then we will always have a point where the derivative is 0. It's possible that your function could be like this. There's never a place on that function where the derivative is 0. Okay? But we don't have a change in direction. What we need in this case, and notice here the conditions, all right? You have to pay attention to conditions when you're looking at a theorem. First of all, we lay out 2 conditions in this first sentence. So let f be continuous on the closed interval from a to b, and differentiable on the open interval from a to b. Okay? So the question you were asking about the endpoints, if this did happen to be an endpoint, that's still okay, as long as it's defined at that point.
Wait, I'm sorry, this question goes way back.
So those are the first conditions, but then look at this. It says if f of a equals f of b. In other words, these y coordinates have to be the same. Then there's at least one number c in the interval from a to b such that f prime of c equals 0. All right? So we're saying that if you start at a particular value and you end at that same value, then somewhere in the middle there the derivative has to equal 0. Okay? Because either you never change direction and you just stay at 0 the whole time, or if you change the value, you've got to change direction somewhere in there to get back down to the original value. Okay? If you start going up, you've got to change and come back down. If you start by going down, you've got to change direction and come back up. And every time you change direction, the derivative is 0. Okay? That's kind of a very informal proof. Okay? Wouldn't even really call it a proof, but that's the idea. Okay? So, let's look at actually using this here. It says, illustrating Rolle's theorem, let f of x equal x squared minus 3x plus 2. Show that f prime of x equals 0 at some point between the two x-intercepts. So the first thing that I would do is find the x-intercepts. Alright, so the x-intercepts are where what happens? Y equals 0. Alright, so we let this equal 0, x squared minus 3x plus 2 equals 0. So we're finding the x-intercepts here. And I factor this. What's this factor into? There we go. So our x-intercepts are at x equals 2 and 1. So now one temptation is going to be just to go ahead and find where the derivative equals 0, okay? But the problem specifically asks us to use Rolle's theorem here, okay? And it actually does not ask us to find what that point is. All it says is to prove that it exists, okay? Prove that there is a point where the derivative equals 0, okay? So we've got a couple of things here that we need to do to prove this, all right? One, and we think back through Rolle's theorem, the first thing that it said is that it had to be continuous and differentiable over the interval. Well, now we know what interval we're talking about. We're talking about the interval from 1 to 2, okay? So how do I know that f is both continuous and differentiable, not just for this, but for all real numbers? What'd you say? It's a parabola.
Doesn't that prove it in the first place, though? Do you need to do the math behind that? It's a parabola, so there's
Well,
nothing you can do behind it, right?
yeah, we know that this is going to happen. We know it's going to work. Okay? But we're using a very simple one, a parabola, to illustrate the idea. Okay? So that's the first thing. Our conditions are met. The next condition was that f of a had to equal f of b. So I need to do f of 1 and I need to do f of 2. Well, what's f of 1 equal? 0. What's f of 2 equal? 0. Because the way we found those is by plugging in 0 for the function. Okay? So now I know that my endpoints have the same y coordinate. So as a result, by Rolle's theorem, we can say there is at least one value, or we could say C to use the notation of the theorem. There is at least one C in the interval from 1 to 2 where f prime of C equals 0. Okay? We're guaranteed to make that, for that to happen. Okay?
When we use brackets versus parentheses, like it says like in the bottom use parentheses, but in the top use brackets.
Well, there I used brackets because 1 and 2 are included in this interval because I want the endpoints to be the same. But I know based on the theorem that it says on the open interval there will be a C. Okay?
Oh, okay. So then that means just without the brackets.
Yeah. let's run through one more, a little bit quicker this time. Okay, illustrating Rolle's theorem, let f of x equal x to the fourth minus 2x squared. Find all the values of c in the interval from -2 to 2 such that f prime of c equals 0. So this time they actually want those values, however many there are. Okay? So, we do need to illustrate Rolle's theorem, but they gave us the interval. So, first of all, is f continuous and differentiable?
Yes.
How do we know?
Because it's
The rules
what
here.
is it, what do you call it?
You got this, Joe. We believe in you.
We really think that
It doesn't have any holes, doesn't have any asymptotes. Why do we know that?
Because it's not.
differentiable.
Because what?
Because of Rolle's theorem.
No,
Well, one like, well, this.
it's not a quadratic, it's a
It's unholy. Poly.
it's a polynomial, okay?
That's the word.
It's a polynomial.
We love you, Peter.
And we learned this a while ago that all polynomials will be continuous for all real numbers. Okay? And they'll also be differentiable because we know polynomials don't ever have any sharp points or asymptotes or holes. Okay? So because we recognize what that function is and all the properties that go along with that, we know that it'll work here for Rolle's theorem. So the next thing we got to do is find f of -2 and f of 2. Now on the previous one I just wrote down 0 because that's where we got those values in the first place. But here we need to actually plug them in and show the work. When you're told to illustrate a particular method or to show something is true, you want to make sure that you actually show your work. Okay, just like proofs in geometry, you showed every step. So here I'm going to plug in a -2 to the fourth minus 2 times -2 squared. Okay? And I also have a 2 to the fourth minus 2 times 2 squared. So I have 16 minus 8 is 8. And down here I have 16 minus 8 equals 8. So
The y value is the same.
the y value is the same. F of -2 equals f of 2. So I've got that condition met, I've got that condition met. Now I know by Rolle's theorem there has to be at least one value. Okay, so now let's find it. Now let's find it. Alright, so there has to be at least one C. Okay? So let's find it. F prime, we'll come over here to the side. F prime of x is 4x cubed minus 4x. And I can factor that into a 4x times x squared minus 1. So if I'm setting that equal to 0, what does x equal?
0 radical 1 plus or minus 1.
Plus or minus 1. Okay? Are all three of those in the interval that we're looking at?
Yes.
Yes.
So it changes.
So C is 0, 1, or -1. There are actually 3 locations in this case. Do be careful that you don't call something a C if it's not in the interval. If we had had 0 and plus or minus 4, then 0 would have been our only C in this instance.
Why didn't we call it C?
That's just what whoever made this up decided to call it.
Critical number.
Okay?
Curriculum.
Maybe, yeah. Maybe for critical value or something.
So how do you know the all before this is continuous and differentiable?
Because it was a parabola, which is a polynomial. So, same thing as this one.